outside of mathematics, especially kids, ask me what I'm doing, I usually answer that I make Pokemon or Final Fantasy. Actually, I work with companies making these animation films and video games. Here's overview of what I do in application side. And I'm not going to talk about them today, but if you find something interesting here, please ask me later. I will be very happy to talk about them. For example, these things look very different from pure mathematics, but actually, for example, this octopus on the left, to move this octopus, I use the Hodge theory on simplicial cohomology. So it's very mathematical. It's interesting as theory as well. Okay, today's topic is linkage mechanism. This is something between applied mathematics and pure mathematics. Okay, what is linkage? Linkage is a collection of rigid bars connected by so-called ball joints. And you are now looking at 3 typical examples of linkage system, linkage mechanism. For example, the center one, have you ever considered how wiper works? And in fact, it's not very probably clear from this animation, but to move wiper, you need only one motor which rotates in one direction at a constant speed. And using this kind of simple mechanism, you can convert this rotational motion of the motor into, how can I say this, back and forth motion. And similar idea is used in so-called Watter's parallel motion, which led to the Industrial Revolution. This linkage converts, this linkage on the right, it converts piston motion of the piston up and down into rotational motion of the wheel. And it is used in James Watt's steam locomotion. And mathematically, this kind of linkage is modeled by graph embedding. You have a finite simple graph, and edges are assigned length. Okay. This is abstract linkage, and its realization is an isometric embedding of this graph into some Euclidean space, typically R2 or R3. So for each vertex represents each joint. Okay. So you want to assign coordinates of that joint in, say, 3 space, and then constraints are given by the length of the linkage, the links bars. So 2 joints, the distance of 2 joints are fixed by the bar connecting them. So the space of all possible realization of a given link is defined by the set of real solutions to a system of quadratic equations. Here, quadratic equations are that dictates the length of links, the length of bars. Okay, and this object is studied in mathematics for long time, from Euler to Thurston. And one big theorem about linkage, the configuration space, the state of the space of all states is given by Kempe, but he claimed he gave the proof of his theorem, but actually it was found to be false. But anyway, now this theorem is called Kempe's universality theorem, which states that this is about planar linkage. So it's about linkage in R2, two-dimensional Euclidean space. And this theorem states that any bounded plane algebraic curve can be traced by some linkage. In other words, more casual words, this theorem assures that there is a linkage which can sign your name. And this theorem was first proposed by Kempe in 19th century, but it was found to be wrong and proved actually recently in 21st century. An interesting historical remark is this Kempe is famous for the wrong proof of four colors theorem as well. So he is a very creative person. He found many interesting theorems, but his proofs were sometimes incorrect. Okay, so what we want to know is the topology of this configuration space, the space of all states of a given linkage. And this is a very simple example, but illuminating example. So let me talk about this special case. You have 3 joints connected by 2 bars, and 2 joints are fixed to the wall. Okay, and the distance between 2 walls is 2h, 2 times h, and the length of the bar is L. Okay, then what is the configuration space? Okay, when the length of the bar is long enough, more than half of the distance between walls, then you have S1 circle. This is 3-dimensional linkage. So you have joints, and this center joint, X2, moves on a circle. And when L is equal to H, exactly H, then you have 1 point, just this center joint can't move. When L is too short, then you have no solution. So the configuration space is just null space. So depending on the parameter, you have different topology with the configuration space. And this is what we want to see. Okay. But now, yeah, I will introduce Kaleidocycle. Probably many of you have seen this toy or origami. And mathematically, probably it's interesting because it can move. It's not a polytope, but it's kind of a generalization of polytope, and it moves. And famous Cauchy's rigidity theorem states if you have a convex polytope, then you can never move it. It has no flexibility. Convex polytopes have no flexibility. And also Bellows, so-called Bellows theorem, states that if you have a concave or convex polytope, and when it's flexible, even when it's flexible, you can't change its volume. And this polytope, this generalized polytope, Kaleidocycles, follows this Bellows theorem. Okay, so now how this Kaleidocycle can be considered as a linkage. The simple way is to consider each vertex of this tetrahedra as joint and each edge as rigid bar. So you have 2n joints. N is the number of tetrahedra. You have 2n joints, and 5n bars. This is one way to look at Kaleidocycle as linkage, but you can also look at it as so-called hinged linkage, consisting of hinge joints. Hinge is a special type of joint which allows only, okay, I have a picture here. So, hinge has axis of rotation and two rigid bodies connected by hinge can change only, they have only 1 degree of freedom. They can turn only around the fixed axis. And this time, this hinged linkage can be modeled by, again, a type of graph embedding, but this time, the vertex corresponds to not a point in R3. Okay, here we consider only R3, but the vertex corresponds to each joint hinge, and hinge is embedded as lines in R3, not just point. So you have each embedding is you have a collection of lines, affine lines in R3, and of course you have some constraints. First, the hinges, adjacent hinges connected by some rigid body, they have fixed distance, and also they have fixed angle. Two adjacent hinges has to have fixed angle. Basically, you can't change the shape of tetrahedra. Okay. Anyway, this hinged linkage can be modeled again by a graph, and its realization is given by the collection or arrangement of affine lines in R3, satisfying certain relation, geometric relation constraints like distance and angle. And angle can be written by the inner product, so it's quadratic. And also distance is quadratic. So you have system of quadratic equations. Now, again, this configuration space, the space of all realization, all states of given hinged linkage is specified by the real solutions of a system of quadratic equations. So it's a real algebraic variety. And actually, it's a sub-variety of the product of affine Grassmannians. Okay, now in this setting, I want to give a generalized Kaleidocycle, definition of Kaleidocycle as a mathematical object. Okay, okay. Do you have any question? Go ahead. No? Okay. Do you have any question?
Okay.
Okay, let me continue. Okay. So in this setting, any Kaleidocycle, n is an integer or natural number, is closed hinged linkage. Closed means underlying graph is just a circle. Closed hinged linkage. And all the distance and angles are same. So basically, intuitively, it is like this in the picture. So you have n copies of congruent tetrahedra, and they are connected by edges. Okay, now I'm going to give another mathematical description of this Kaleidocycle. Actually, this is now I just defined it as hinged linkage, special kind of hinged linkage. But if you look at the center curve of the tetrahedra, so how do you get this center curve? You connect the midpoint, center point of each hinge, and you get polygonal circle. And you can actually identify any Kaleidocycle just by this central polygonal circle. So there is one-to-one correspondence between this, I call it discrete space curve, is polygon in 3 space. Discrete space curve and Kaleidocycle. And this discrete space curve, because each tetrahedra, all the tetrahedra have the same shape. And if we translate this, into curve language, this shape of the tetrahedra is encoded as so-called torsion of the curve. I will give the definition of torsion later. But anyway, and okay, and another correspondence is this hinge corresponds to so-called binomals of this discrete curve. Binomial is just the direction of the line, which is orthogonal to two consecutive tangent, the direction of polygon. Okay, this is just definition of strip or discrete curve in continuous setting. Okay, it's just remark. We are just interested in discrete version of this, but probably this continuous version is more familiar. So I will record the definition of continuous space curve and continuous strip first. So let gamma be a map from closed interval 0 to 2 pi to R3, and with constant speed, which means the derivative is constant 1. And then its normal vector can be defined as a function, again from defined over the closed interval 0 to 2 pi to S2, because it's just specified the direction of the vector on the curve. And why it is called normal? Because it is orthogonal to the tangent direction. Tangent direction is just the derivative, first derivative of the curve. Okay, and this object is called strip. And when it's closed, meaning that the starting point and end point are the same, then it's called closed. And also to close the strip, you also have to have this condition. The normal direction should be same at 0 and 2 pi, or it's negative. So basically, you have gamma, and on each point on this gamma, this closed curve, you have normal vector. So you have a strip like this. And at the starting point, you have to have the same direction or opposite direction to close the strip. Okay, this is continuous version of strip. And okay, I will probably skip this. And its discrete version is very similar, just you have discrete curve, which is just polygon instead of continuous curve. And at each vertex, you have normal vector, which is orthogonal to adjacent tangent directions. So if you look at the center curve of the Kaleidocycle, then this normal direction is given by the hinge direction, because hinge is always orthogonal to the adjacent central direction. Okay. So actually, this special normal direction, in discrete case, it's actually, if you require this normal direction to be orthogonal to both edges, adjacent edges, then you have, in general, you have only one direction, or negative, it's negative, which is binormal, which is called binormals. Anyway, yeah, this is kind of correspondence between linkage and discrete space curve. And with this language, okay, here I wrote modularized space, but it's just configuration space. The configuration space of Kaleidocycles can be described by a system of quadratic equations like this. So first, okay, here we need one more thing. So instead of starting, so to consider space curve, you can directly think of polygonal curve, or you can also start with set of binormal directions, and then you can recover the original curve by taking this exterior product of two binormals, because binormals are orthogonal to tangent directions. So if you take cross product of two binormals, then you get tangent direction between them. Of course, here we need some generality assumption, which means if you have three collinear points on the curve, then you can't do this. But let's assume all three consecutive points are not collinear. Then you can always convert from central line to binormal directions. This correspondence is called Darboux correspondence. So basically, it says considering polygonal curve is equivalent to considering binormals, set of binormal directions. Okay, then instead of using coordinates of vertices, polygonal curve, we can use binormals as our variables. Then the geometric constraints for the linkage becomes simpler. First, maybe the third one is easier to think. So the third one about inner product. So two adjacent hinges or binormals should have a constant angle, so that their inner products are constant. And also the length of the binormals are normalized to 1. This is quadratic equations. And the second one is about closedness of the central curve. So if you reconstruct the central curve, the discrete space curve from binormals, then the curve should be closed to form Kaleidocycle, because by definition, Kaleidocycles are closed ring. And for that, you have to have this equation. The sum of cross products is 0. You have to come back to the original position. So you, again, this equation is quadratic. So the configuration space of Kaleidocycles is identified by the real solutions of these quadratic equations. And actually, we want to mod out the rotational symmetry by SO3, because if you have something in space, then you can move without changing its shape. But we are not interested in this motion. We want to fix one place and want to see how, okay, this is rigid body, so I can't move it. Maybe, yeah, this kind of thing. You can move around in the space, but what we are interested is this kind of motion, which changes the shape. So to kill the global motion, we want to mod out this rotational symmetry given by the SO3 special orthogonal group, or 3-dimensional special orthogonal group. So this is our target. Yeah, please.
So a kaleidocycle, it's a little bit more than a framed curve, right? Because it's actually made out of a specific material, so it has a concrete width, and it can't intersect itself in space, for example.
Yes.
In your modular space, it seems like the things can go through each other and intersect themselves.
Yes, exactly. Yeah, that's important point. Yes, thank you very much. Yes, I ignore collision.
Excuse me.
Mm-hmm.
Here in the Kaji cycle up to scaling, so you've written that P naught is equal to Bn if this if the graph is oriented. So that means in this case it will be like closed, and if the graph is not oriented, then B0 is gonna be minus, then it will be open on both sides. Is that what you mean? When
Yes,
B naught
we
is
have
equal to
actually
Bn
we
and
have
B naught is
two.
equal minus
Yes.
Pn.
Both of them are allowed. So we have actually two disconnected components to the solution space. You can read this condition as or. B0 should be Bn, or B0 should be minus Bn.
Yes. So okay. So if when it's Bn, this means the first point will be connected to the last point. Yes. Otherwise, they will not be connected.
So when Bn is equal to negative of B0 is B0 equals to negative of Bn, then you have something like this. So after one turn, when it comes back, you have opposite direction. Like, Möbius band. You know what is Möbius band? Möbius strip? Okay. For example, this is actually Möbius strip. Oh, it's difficult. Oh, sorry.
Yes. So it will be like this. So this is the case when P naught is equal to minus Bn, yes? For this strip.
Yeah. For Möbius strip, you have B0 is minus Bn.
Yeah, okay. Yeah, okay,
Thank you. Yes, thank you. Anyway, yes, I think I have to emphasize this fact. Here, I ignore global collision. Okay, so we kind of idealize the setting. So actually, if we make our tetrahedra very thin, then you don't have to care about collision. So let's say now our tetrahedra is very thin, like 0 length, for example. Actually, we can set it to certain finite length for any n, but let's assume that we have 0 very thin strip or tetrahedra. Okay, now what we want to know is the topology of this configuration space. And this motion of Kaleidocycle, this turning over motion corresponds to the a one-dimensional subspace of this configuration space. Okay, one point in configuration space corresponds to one specific state of Kaleidocycle, like the left picture. And one-dimensional subspace of this configuration space, solution space, corresponds to circular periodic motion of a Kaleidocycle. Okay, and what we are interested in is okay. Before that, I want to introduce some topological invariants of strip, which is called writhe and twisting, and it is defined in this somewhat complicated double integral. But the important thing is these two values are defined for each strip, and they are not actually topological invariants. They are conformal invariants, but the sum of them becomes isotopy invariant, topological invariant. And actually this twice the sum is equal to the number of half twists. So you have maybe the Möbius strip has one half twist, and sometimes you have 3 half twists, maybe strip. But anyway, this the number of twists can be decomposed into 2 factors. Each of them are not isotopy invariants, but just conformal invariants. And we have discrete version of same statement. And Kaleidocycle, especially non-oriented one. So from now on, we only consider non-oriented Kaleidocycle. Actually, there is one-to-one correspondence between oriented Kaleidocycle and non-oriented Kaleidocycle. So we just look at non-oriented one. We focus on non-oriented one. Okay, and what I wanted to say by introducing these invariants is that for a curve or discrete curve to be closed requires a lot of things. I mean, there is very strong topological constraint for a curve to be closed. So for example, if you specify, okay, a space curve is specified by curvature and torsion, which is the result of classical Frenet-Sellet theorem. But if you specify, for example, just curvature, then you have freedom for torsion. But to make it close, it's very difficult. To make a curve with a specified curvature, which is closed, is difficult because of this kind of quantized invariant. This sum of twist and writhe takes values in half integer, so it's quantized. Okay. And these topological constraints lead to interesting properties of Kaleidocycle. For example, this is just actually conjecture, and I have no proof yet. But look at the last line. For example, there seems to be no Kaleidocycle with less than 3 half twists. The minimum number of half twists is 3. There's no usual Möbius strip with 1 half twist or two half twists. And I'm trying very hard to prove it, but for now, up to now, I failed. Okay, okay, let's skip this. Okay, now let's go back to the topology of configuration space. The first question about the topology of this configuration space is its dimension. Okay? And the dimension of real algebraic variety is very difficult to figure out, but there is very simple estimate just by counting the number of variables and number of equations and take the difference between them. And if you do this calculation, then you get actually n minus 6, the dimension or the number of variables minus the number of equations is n minus 6, sorry, n minus 6. So in general, you expect that the dimension of this configuration space is n minus 6. But of course, there are many exceptions. For example, the classical 6-fold Kaleidocycle, the classical one has 6 tetrahedra. So this equation gives 0 mobility, 0 dimensional configuration space, which means you can't rotate it, but actually you can rotate it. So we can say that there is one redundant equation in the defining equation of this Kaleidocycle, 6 Kaleidocycle. Okay, this happens also in complex algebraic geometry, this redundant equation. But the opposite thing is actually very peculiar to real algebraic variety. If you have bigger n, then you would assume that you have bigger dimensional space for that solution. But, okay, but here's a conjecture. Actually, I have, again, no proof for this fact, but this is just a conjecture. So for a specific value for the angle between two adjacent hinges, actually that is the minimum angle for the Kaleidocycle to exist. Okay, so now I'm interested only in non-oriented case. So if you want to make a closed strip, which is non-oriented, then you have to make a half turn, at least a half turn somewhere. So you have to have angle between two adjacent hinges. Otherwise, you just get a cylinder, right? And we are interested in the minimum angle between two hinges, which can close. Okay, and this minimum number can be numerically computed easily using Mathematica or Maple or whatever. And if you take that value and consider the space of configurations, solutions, then you always get S1, so one circle. In particular, its dimension is 1. So by counting the number of variables and equations, you have to have n-6 dimensional real algebraic variety. But for the specific, this singular value, you get only one-dimensional space. And this is very peculiar to real algebraic variety. For complex algebraic variety, you never get this, this kind of situation. And this is actually explained, that the simplest case can be explained using the simple example I gave in the beginning with 3 joints between 2 walls. Okay, anyway, this is just a conjecture, and I have no proof yet, but Okay. I have to say this is joint work with Johannes Schenke, and we filed a patent for this result. So mathematically, this is just a conjecture, but for patent, we don't have to submit proof. So we just filed a patent first because it's useful for as a linkage. You want to have one-dimensional degree of freedom always for designing linkage, because otherwise you get unexpected motion, wobbling motion, for example, if the degree of freedom, the dimension of the solution space have dimension greater than 1. So having one-dimensional configuration space is very important practically, so it can be a patent. But unfortunately, this was published by Schenke and some other person in a actually very good journal, but I'm not very happy with what they did. But anyway, this is just a, mathematically, this is just a conjecture. So you are welcome to solve it, to prove it. I think it's very interesting, but it can be very difficult because it involves real algebraic variety. Okay. How many minutes do I have? Oh, okay, maybe 5 minutes. Okay, now I will talk about more mathematical thing with some proofs. Now I want to analyze this turning over motion, rotating motion, or everting motion of Kaleidocycles. Okay, so as I said before, Kaleidocycles are identified with discrete space curve. Okay, and its motion, how about its motion? Its motion is identified with so-called isoperimetric deformation of the space curve. What is isoperimetric? Isoperimetric means the length doesn't change during the motion. And these Kaleidocycles are discrete curves with constant torsion. And its isoperimetric motion preserve length and torsion. This is what we want to find, or how we model the motion of Kaleidocycle in a mathematical setting. And for continuous curve, it is known that these isoperimetric motions are described by MKDV equations. It's partial differential equation, certain partial differential equation. So we can expect that there is a discrete analog of this MKDV equation, which describes this motion of discrete curve. Okay, and perhaps I skip to the main theorem. And this theorem is obtained with Kajiwara and Park, which states that basically we can discretize MKDV equation to obtain constant torsion isoperimetric deformation of discrete space curve. And also we can get discretization of Sine-Gordon, another PDE called Sine-Gordon equation to describe this motion of Kaleidocycle. But I don't think I have enough time to go into details. But the important thing which I want to emphasize is that there is discrete analog of curve deformation theory, which describes the motion of this linkage Kaleidocycle. An interesting thing is, for continuous case, you don't have any algebra, just a smooth manifold. But for discrete case, we have this configuration space was real algebraic variety. And over this real algebraic variety, you have integrable system, kind of discrete version of partial differential equation over real algebraic variety. And that equation generates one-dimensional orbit in the real algebraic variety. So I think that the result is very interesting, which connects real algebraic geometry and integrable system. And this result is proved. Okay, so here is the motion generated by MKDV equation. Yes, and okay, on that, maybe I will skip this. And one good thing about describing this motion in terms of integrable system is that integrable systems are physically nice. They have very good properties like conservation laws. So we have a lot of quantities which are preserved during that motion, and we can extract that information from the equation. Yes, maybe. Yeah, I think it's time. So I will stop here. But yeah, to summarize, we have, on one hand, we have a linkage system, which is a subject of mechanical engineering. And at the other side, we have discrete theory of discrete curves and discrete integrable systems. And we have good, nice correspondence between them. Okay, thank you very much.